Trishalini Kalachelvan and we are from Group 3. So today our group going to present the topic of diagonalization. There are 3 theorems in this topic and let's go through each of them. But before that, let me introduce my teammates. That's me, Trishalini, and Nadia Natasha, Rashmika, Shazika Hasbin, and Ki Hushuan.
Okay, let's dive into theorem 1. Let A be an n times n matrix. Then A is a diagonalizable if and only if A has n linear independent eigenvectors. More precisely, we can say that there exists in n by n invertible matrix P and a diagonal matrix T such that inverse of P times P equals to A. If and only if the column of P are n linear independent eigenvector of A, and the diagonal entries of D are the eigenvalue of A corresponding to eigenvector in P in the same order. There are 4-step diagonalized and n times n matrix A equals to P times D times P inverse. So first, we will find eigenvalue of A. Second, we will find n linear independent eigenvector of A. Third, we construct P from the vector in step 2. And fourth, we will construct D from the corresponding eigenvalues.
Next, I will show an example question related to theorem 1. Diagonalize the following matrix. So, the step 1 is to find the eigenvalue. Calculate the eigenvalue of A using the determinant equation that A minus lambda I equal to 0. Next, you can calculate for the depth A minus lambda I, and you will get the 3 lambda, which is 6, 3, and 2. Step 2 is to find the eigenvector. For each eigenvalue, solve A minus lambda IV equal to 0 when lambda equal to 6. Next, reduce the matrix to row and reduce echelon form, and you will get x1 as a free variables, x2 is equal to 0, x3 equal to 0. So you will get the v1 is equal to 1, 0, 0. Same goes for the other lambda. When lambda is equal to 3, you will get the v2 equal to negative 2 over 3, 1, and 0. When lambda is equal to 2, you will get the v3 equal to negative 3 over 4, 1, 1. Step 3 is to construct P and D. Matrix P is formed by placing the eigenvector as column, so you will get the P. And matrix D is the diagonal matrix with eigenvalue of the diagonals. Lambda 1, lambda 2, lambda 3, and v1, v2, v3 are chosen freely and do not follow any strict rule, but make sure the order of the lambda in D matches the column of V in P. Last is to check the work by verifying AP equal to PD. When you calculate the AP and PD, you will get the same answer, which is 6, negative 2, 3 over 2, 0, 3, 2, 0, 0, 2. So you can say that the matrix X is diagonalized into P and D.
So now I want to talk about theorem 2. For the theorem 2, let A and n by n matrix. So the matrix A with n distinct eigenvalues is automatically diagonalized. We have 5 steps to do a diagonalize for distinct eigenvalues. For the first step, we have to find the eigenvalues with determinant A minus lambda I equal to 0. So if we get all distinct eigenvalues, which is lambda is different, the matrix A is diagonalized. And then when we get the lambda is different, which is mean we have to try theorem 1 to determine whether the matrix is diagonalized or not. And then we can continue to the other step, which is find the eigenvectors and form matrix P and do a diagonalize.
Next, I'm going to show you some examples that are related to theorem 2. The first example, given matrix A is equal to 5, 4, 1, 0, 3, 0, 2, 1, 6. Calculate the eigenvalues of A using the determinant equation, determinant A minus lambda I equals to 0. First, find A minus lambda I, and then you get 5 minus lambda, 4, 1, 0, 3 minus lambda, 0, 2, 1, 6 minus lambda. And then find the determinant, and then you'll get 3, 4, 7. Since all the 3 eigenvalues are distinct, the matrix is diagonalizable. The next example, given matrix B is 4, 0, 2, 0, 4, 0, 0, 0, 3, calculate the eigenvalues of B using the determinant equation, determinant B minus lambda I equals to 0. and then find the b minus lambda I, and then you get 4 minus lambda 0, 2, 0, 4 minus lambda 0, 0, 0, 3 minus lambda. And then find the determinant, and then you get the eigenvalues, which is 4, 4, 3. Since there are two same eigenvalues, try theorem 1 to determine whether the matrix B is diagonalized or not.
Let's talk about the final theorem of this topic. We can see that there are three main conditions for this theorem. Let's go one by one. The first statement states that the dimension of eigenspace for each eigenvalue can never exceed its algebraic multiplicity. But what is algebraic multiplicity? It means the number of times the eigenvalue appears in the characteristics polynomial. Not only that, the second statement states that the dimension of eigenspace that corresponding to each eigenvalue must be equals to its algebraic multiplicity. For your information, the dimension of eigenspace is actually equals to geometric multiplicity. What is geometric multiplicity? It means the number of linearly independent eigenvectors that corresponding to each eigenvalue. And lastly, if the matrix is diagonalizable, then the eigenvectors will form a complete basis for Rn. For a clear visualization, give a look at those examples. And that's all from us. Thanks for watching.